we have discussed calculating the Z transform. So we have taken examples of causal sequence and anti-causal sequence, and we have calculated the Z transform of both. Now, in case of causal sequence, we took the examples of unit step function un with multiplied with a to the power n. And in case of anti-causal signal, we took the anti-causal sequence u minus n minus 1 multiplied with minus a to the power n. So in those two cases, the Z transform gave us 1 by 1 minus AZ inverse. Okay. So that can be visible, that can be seen from the table. Z transform table, it is given. You see that this arrow, okay, this is time domain sequence a to the power n un, whose Z transform is 1 by 1 minus AZ inverse. Another anti-causal sequence, it is minus a to the power n u of minus n minus 1, 1 by 1 minus AZ inverse. Now note the ROC for these two cases. The ROC is mod Z greater than A or mod A. That is for causal sequence. So exterior of a circle of radius A. Okay. Mod Z greater than A, because Z is a complex number that is equal to R into e to the power j omega, where radius R is a phasor representing phasor rotating at frequency omega. Okay. So its radius is R, so R is greater than A. Okay. So that is exterior of a circle, a region outside of a circle. Similarly, for anti-causal sequence, the ROC is interior of a circle of radius A. Okay. Mod Z less than mod A. So these things have to be kept in mind always throughout the study of this subject, signal processing. Okay. Anti-causal, causal, anti-causal. In case of causal, exterior of a circle. In case of anti-causal, interior of a circle. Those ROC. Okay. Now, coming back to the problem we discussed earlier, that you might see these examples in many competitive exam also, that they take one exam signal b to the power mod n. Okay, b to the power mod n. So for this case, what should be the shape of signal? For this case, shape of the signal is actually when n is negative, that time it is only b to the power n. Okay. So if b is less than 1, then it is decreasing like this, okay, this case. And for the causal anti-causal part, okay, anti-causal part is b to the power minus n u of minus n when n negative. Okay. So b is less than 1. So it is so b to the power minus n, okay, when n is negative. So you see that it is when n is say minus 1, okay, n is minus 1, so it is 1 by b. Okay, here at this position n is equal to minus 1, it is 1 by b. So if b is less than 1, so some high value, okay, then if n is minus 2, so minus 2, n is minus 2, that means 1 by b square at n is equal to 2. So 1 by b square, and b is less than 1. So their multiplication is also less than 1. Okay. So we will get value. So this way we plot this signal and we get for two case, okay, b less than 1 and b greater than 1. Okay. Now for these two case, Z transform is what? B to the power n un. So it is 1 by 1 minus bz inverse, okay, because it is simply in step sequence. And this case, b to the power minus n, u of minus n minus 1, anti-causal part. So here, according to the formula, it is if minus a to the power n u minus n minus 1. This is the formula. So in place of a, we assume that a is equal to b to the power minus 1. It means 1 by b or b inverse. B inverse. So, and that was also negative of minus a to the power n u minus n minus 1. So that's why due to that negative, here negative comes because it is not present here, negative is not present. So we see that here it is uh, minus 1, 1 minus, it is also AZ inverse, but in place of A, it is B inverse. Okay. And since it is causal sequence, so anti-causal sequence, so it is interior of a circle of radius 1 by b, radius 1 by b. So mod z is less than 1 by b. So we get that z transform as 1 by 1 minus b z inverse plus minus of 1 minus b inverse z inverse, and the ROC is mod z greater than mod z less than 1 by b, and greater than 1 by b, and here actually that thing is wrongly written because z is greater than b, so it is just opposite. Okay, here some some drop or mistake is there. So no problem. It is taken from some other here. But you should know that the reason what should be the Z transform of this, and you should try to find out and give me the correct answer. Okay, calculate the correct answer and should show me. Who will show? Then I'll be very happy, okay, to see the correct answer. Okay. Now this there are some formula for Z transform. Okay, here some tabular formula is there. So now you see that some properties are also there. Since you are supposed to study in previous earlier semester, so now I am not going in details, and these are also being similar to Fourier transform. Okay, so like say linearity, then time shifting. Time shifting is if you delay one's time domain signal by k, in z domain it is multiplied with z to the power minus k. Okay, and z scaling, if z domain is multiplied by a inverse, then in time domain it is a to the power n. Time reversal, if time it is x of minus n, then in z domain it becomes x of z inverse. Similarly, differentiation, okay, nxn. If you take the z transform, it is actually minus z dx z dz. Okay. And in convolution, it is convolution in time domain sequence leads to multiplication in Z domain. Okay. So this is the some properties of Z transform. Okay. Now, now you see that inverse Z transform.
Sir,
Inverse
actually
Z.
slide number 10 is visible.
Huh?
Slide number 10 is visible, sir.
Slide number 10. Slide is not changing.
Yes, sir. It is at slide number 10 only now.
Okay. Now it is changing.
Yes, sir.
Okay. So it is that property I was discussing about Z transform that let me do that mode. Window mode, desktop, entire screen, then it will be better. Entire screen. Yes. So we are discussing the property that time shifting. If you delay the time domain signal, then Z domain it is multiplied with Z to the power minus K. Time reversal is Z domain, Z variable change to Z inverse. Then I'm not discussing what about the effect in ROC because they take a lot of time, okay, to explain. Simply just go through this one, and these are the concepts that will be used to understand the remaining other topics. So in convolution, when we multiply the two signal in time domain, in Z domain, they when we convolve two signals, x1 convolution x2, then in Z domain they get multiplied. Okay. So now let us do the inverse Z transform. Inverse Z transform is what? There are three methods. One is Cauchy's residue technique or contour integration, then power series method or long division method, and third one is partial fraction expansion and table lookup. So I will only discuss the third one, okay, partial fraction expansion. These other two are written in the slides. When you will get time, you just go through it. Okay? Because these two are only to solve, okay, the inverse transform. But the partial fraction is widely used, okay, because this is easy to remember. Okay, so I discuss take this example. Okay. So power series method and you just go through it is clearly explained. Okay. When you go through it, you will easily understand what is how the these are used. But what is the advantage that only first few samples are obtained. Just directly we get the sequence. Okay, final sequence we get, but we get only the first few samples. So this is the drawback of fast method. That is not fast method. It is power series method. Then the third one is the partial fraction expansion. So are you aware of this partial fraction expansion method?
No, sir.
No, sir. We know about the partial fraction mathematically, sir, but not the method.
Okay, fine. So here you see that let us take one ratio of the Z transform of any sequence, that is xz. Okay. Xz is the ratio of numerator by denominator. So ratio of two expression. One is called numerator, the lower one is the denominator. And you see the power or order of the expression z in both in numerator and denominator, m and n. So m and n may be same or higher or lower, may be dissimilar. So if m is higher than n, that means order of the numerator is higher. In that case, first step, so that time it is called improper rational function. Improper rational function. Like the examples it is seen here. In the numerator, the expression is 1 plus 3z inverse plus 11 by 6 z to the power minus 2 plus 1 by 3 z to the power minus 3. Okay. Then 1 plus 5 by 6 z inverse plus 1 by 6 z to the power minus 2. Okay. So this is numerator has the order higher than the numerator. So what we will do, you have to convert this to proper rational function. Proper rational function means the numerator order should be lower than the order of the denominator. So the simple method is you have to divide this one. Okay? You have to divide this one by this way, and you will get the proper rational function. So first you see that how we will convert that we take the divisor and dividend. Okay? So it is but here the way we write that written in reverse order to eliminate higher order term. So higher order terms are written first. So 1 by 3 z to the power minus 3 plus 1 by 6 z to the power 11 by 6 z to the power minus 2 plus 3 z inverse plus 1. And here also we write this way. So if you divide this, then you see that this way, if you multiply this, so 1 by 3, 1 by 6 is there. So you have to multiply it in 2z inverse. So 2z inverse we get that 1 by 3 z to the power minus 3 plus 11 by 6 z to the power minus 2 plus 3z inverse plus 1. Okay. So if you go on dividing this way, you'll get the expression xz is equal to 1 plus 2z inverse plus 1 by 6 z in. So there are two parts. One part is contains the division, that is one polynomial you will get here, and other part is the proper rational function. So here order of the denominator is this 2 and order of the numerator is 1. So it is proper rational function. Now this is the case when this is needed when the given expression is of improper rational function. If it is proper rational function, then it is not needed. So next case we use that proper rational function. Proper rational function is z to the power. So you see this is given as b0 plus b1 z inverse plus till bm z to the power minus m and 1 plus a1 z inverse up to this. So we multiply both of the terms. Z to the power n. Then to get this in one form, okay, like this way. Okay, so higher order terms. So that means we just removing the inverse of z term. Okay, we just since all terms includes z inverse term, so it sometimes becomes difficult to deal with z inverse. Why not only z? So we multiply this both the numerator and denominator with z to the power n, and we get this way z to the power n, b0 z to the power n plus b1 z n to the power n minus 1, and last term is n minus m, and in the denominator we get z to the power 1 plus a1 z to the power n minus 1, like this. So this is the ratio. Now we take one z. Now divide it with z to make this always proper. Okay. So we take this other way how to make it always proper. Just take one here, this one from this. No, not this. It is not the actual reason. Actual reason is different thing that you will understand, that you have to correlate this with the this is be useful for to find the inverse z transform. Okay. That's how you take this one. So xz by z is, let us write partial fraction this whole ratio by sum of different terms. Okay. Z we have taken from the numerator and comes into the left hand side of the denominator of the left hand side. Xz by z we take. So a1 by z minus. So say let us say that this will have some poles or roots, okay, located at p1, p2 and different values pn, and they are coefficients a1, a2 up to an. So now, so these are the, now after this partial of converting into partial fraction, what we will do later, that actually we will compare these terms with the known formulas of Z transform. Okay, known formulas of Z transform. Then we can easily get the inverse Z transform. Okay. So let us do it with one example, that xz is equal to 1 plus z inverse divided by 1 minus z inverse plus 0.5 z to the power minus 2. So first we multiply the z square. Okay, the higher order terms in the denominator 2z to the power 2. To multiply this z square, so it becomes z square plus z. Okay, the numerator, and in the denominator z square minus z plus 0.5. So since we have to take common z from the numerator and put it in the left hand side, so to make it xz by z, so it becomes z plus 1 divided by z square minus z plus 0.5. Now factorize this expression, we get z minus p1 into z minus p2, where p1 and p2 as the complex conjugate, half plus j 1 by 2, half minus j into 1 by 2. Now, since p1 is not p2, we seek an expression that exit. So this one. So now this is the partial fraction. So this whole thing is written as z plus 1 divided by z minus p1 into z minus p2, and it is written as a1 by z minus p1 plus a2 by z minus p2. So next the method, how it is done. So you see that this, to calculate a1, we have to multiply the whole expression with the corresponding poles or corresponding terms, okay, in the numerator, denominator. So a1 by z minus p1. So if you multiply this with z minus p1 throughout the equation all over, so this will leave only constant a1. So thus a1 it will give. Now in that case, if you evaluate that expression again at that particular pole p1, then other terms will remain 0. A2 will remain 0. Okay. So this we get that a1 is equal to z minus p1 into xz by z. A2 is multiplied with z minus p1, so this term will be 0. Okay. So we evaluate this at z is equal to p1. So we get this one z plus z plus 1. What is that term? That is z plus 1. यहाँ पे मल्टीप्लाई कर देते हैं, ये क्या होगा z plus 1 डिवाइड बाई z minus p2 हो जाएगा. ठीक है. सो इसको वैल्यू बैठाएंगे p1 और p2 का. z is equal to p1 है, p1 का वैल्यू पुट करेंगे तो a1 मिल गया, दैट इज हाफ माइनस j इंटू 3/2. सिमिलरली a2 भी मिल जाएगा. a2 मिलने के लिए कैलकुलेट करने के लिए उसको उसका कॉरेस्पॉन्डिंग जो पोल है, पोल कॉरेस्पॉन्डिंग जो टर्म है डिनोमिनेटर में, उसके साथ मल्टीप्लाई करना है. तो इस तरीके से वो कैलकुलेट हो जाएगा. अब क्या है, poles, we see that poles p1 and p2 are complex conjugate. So the property tells that their coefficients will also be complex conjugate. Okay. A1 and A2, you see A1 is this and A2 is this. Okay, whatever. Now another case is there, that is multiple order poles. अच्छा, ये examples you see it from your side. I will not explain, but some basic property. Like by seeing the poles, how will correlate it to the time domain sequence. So let us so you see that once the ROCs are given, when the Z transform is given, corresponding ROCs are given. Okay. So by seeing the ROC, you have to guess what type of signal it is. If ROC is greater than some value, then it should be causal sequence. ROC is less than some value, it is anti-causal sequence. Let's let's don't go to this all in details. Okay. We just take one example. Just this part you see. This part you see that one signal example is given that xz is equal to 1 by 1 minus 1.5 z inverse plus 0.5 or minus 2. Okay. So here ROC is equal to ROC is mod z. ROC is given as mod z greater than 1. Okay. So how we will find the time domain sequence? Okay. It's very simple. Now, are you able to see this? The example that is written this side.
No, sir.
So now let us take some bigger example, bigger figure. Now are you able to see this one? This one?
Yes, sir. Yes, sir.
Okay. So determine the inverse Z transform of this expression 1 by 1 minus 1.5 Z inverse plus 0.5 Z to the power minus 2. There are three cases. ROC is mod Z greater than 1. That means it corresponds to causal sequence. ROC is mod, same example. ROC is less than some value that represent anti-causal sequence, and ROC lies within some value, within some range that is more than 0.5, less than 1. So these three different cases leads you will yield three different time domain signal, even if the Z transform is same. Okay. So let us discuss the first case that mod Z is greater than 1. So first you partial fraction, get the partial fraction of this. Okay. So after getting the partial fraction, so here actually we will get this as the answer. Okay, I'm not there exactly calculating this, okay, but I have jumped some steps and directly calculated the both methods. You know that how to get the partial fraction. The same method. So A1 and A2 we have got as 2 and 1, and poles are located at this one. Okay. 1 minus Z inverse, then 1 minus 0.5 Z inverse. So how will you identify the causal sequence? Okay. So mod Z, first example is mod Z greater than 1. So if it is mod Z greater than 1, then look at the poles. Poles, one pole is located at 1, another is located at 0.5. So both the poles are both the poles are yeah, this greater than 1, greater than some value. So already mod Z greater than 1, so 0.5 the poles is obviously greater than 1, mod Z obviously greater than 0.5. So both the terms mean causal sequence. So we get 2 into 1 to the power n un because it is alpha z inverse. Okay. So you know that Z transform of a to the power n un. What is it? What is it? Z transform of a to the power n un. Can anybody please tell of a to the power n un?
Sir, Z of
Anybody? It is 1 by 1 minus az inverse. Okay. So 1 by 1 minus az inverse. So here compare with that terms with this. So a is how much now? 1 by 1 minus az inverse. A is the term multiplied with z inverse. So a is how much here?
1, sir.
1. That's why 1 to the power n. Since a to the power n un, so that's why 1 to the power n un would be there. Similarly, the other term, 1 by 1 minus az inverse. Here a is how much? The second term?
0.5.
0.5. So due to this, again it will be 0.5 to the power n or a to the power n, yes, and multiplied with un. Since it is a causal, and you cannot tell by seeing the Z transform. You have to see the ROC. Okay, ROC tells you what should be the signal. If it is interior of a circle greater than some value, and you see that poles are both the poles are located at 1 and 0.5. So obviously both the term represents the causal sequence. Now second term, okay? Second case, mod z less than 0.5. It is given. So if it is your signal, okay, look. So both the poles are located at z is equal to 1 and z is equal to 0.5. Okay. You take the z inverse out. If you write z inverse as 1 by z, so it is z by z minus something. Okay. So poles are located at z is equal to 1 and z is equal to 5. So the question is, if ROC less than 0.5, so you see both the poles are less than that value 0.5. 0.5 is already there, and 1 mod z is also less than, if it is 0.5 less than 0.5, then obviously it is less than 1 also. So both the sequence will represent the anti-causal. Okay, so for anti-causal case, the signal is minus a to the power n un, u minus n minus 1. So minus 2 is there, since it is minus a to the power n un, so it should be coefficient and 1 to the power n minus 2 into 1 to the power n u minus n minus 1. and here already negative is there, so you need not write it. So it is 0.5 to the power n u minus n minus 1. Now two-sided. So first term, so here it is shown that mod z is greater than 0.5 and it is less than 1. So the poles which corresponds to the value higher than 0.5. Okay. The poles which corresponds to higher than 0.5 will represent the associated term with that pole, represent the causal sequence. So which term is associated with the pole which is greater than 0.1, greater than 0.5? This pole, okay? Z minus 1 or Z is equal to 1. This pole and its associated term is greater than 0.5. So this term will represent causal sequence, okay? And this term which is 0.5 less than 0.5, it is told it is less than 0.5, this term. So this term will give you the anti-causal sequence. So this term is 0.5 to the power, okay, 0.5 to the power n u n. So when it is greater than 0.5, so that means exterior of a circle. So that time it is causal sequence. So, where is the term? Yes, this term. So second term represents you the causal sequence. Okay. So it is 0.5 to the power n un because it is according to the condition, okay, should greater than 0.5. So the other pole is situated at z is equal to 1. So that is not, that may be greater than 0.5 but less than 1. So interior of a circle. So the associated term is what? It is the anti-causal sequence. So we have to write it in this way. That's minus 2 into 1 to the power n u minus n minus 1. Okay. So you just go through these examples, okay, and I'm not explaining the Cauchy's residue theorem, but for your interest you can see it is clearly explained there. And if I get time, I may explain later on. Okay. But here, now, what is the time now?
Sir, 11:52.
Okay. Time ho gaya na? I'll upload it. You just go through all this.